Okay, thanks Elaine for the introduction. Hi everyone, I am Lisa and I will be introducing our work, storing and retrieving secrets on a blockchain. And can you guys hear me, by the way? Sorry, I'm just checking. Okay, cool. Thank you so much. This is a joint work with my awesome co-authors, Vipul, Apiram, Brian, and Ivan. And to start things off, let me tell you about some absolutely unrelated applications. So first of all, time lock encryption. It allows a party to encrypt some data and specify a time after which this data can be released. One-time programs allow a person to execute a certain program only exactly once. And finally, fair exchange allows two mutual distrusting parties to exchange their data in a way that either both parties get the data they want or neither of them does. And you might ask yourself, well, Lisa, that's very cool, but why are you telling us all this? Shouldn't we be learning about how to store secrets on a blockchain? And that's a very fair question, and so I will respond. The answer really is that all these applications do have something in common. First of all, they are all very useful, but unfortunately pretty hard to achieve. And second of all, we do know constructions from blockchains and a cryptographic primitive called extractable witness encryption. And extractable witness encryption has been around for a very long time. It has been introduced about 10 years ago. And what it allows you is it allows a party to encrypt a message with respect to a certain problem instance. For example, you can think about some Sudoku puzzle or a bug in an allegedly bug-free program. But generally, this can be any NP statement. And then, given the witness to this problem instance, anyone can decrypt the ciphertext. So given the Sudoku solution, you would be able to decrypt your ciphertext. And extractability is a very strong security property, and it specifies that if you're able to deduce some information about the plaintext, then you should also know the witness. Unfortunately, the issue with extractable witness encryption is that there are no known practical constructions. And what is even worse is that under standard assumptions, we do not know any constructions at all. And in fact, there's some very strong evidence that these constructions may not even exist. So are we back to square one? Do we not have the constructions for all those awesome applications that I introduced earlier? And the answer is no, because in this work, we introduced EWEB, which stands for Extractable Witness Encryption on a Blockchain. And EWEB provides a functionality which is very similar to extractable witness encryption, except that it uses some interaction with blockchain to achieve it. And essentially, if you recall that in all those applications that I introduced earlier, we were already relying not only on extractable witness encryption, but we were also relying on blockchains. And so if you replace extractable witness encryption with EWEB in those applications, you're essentially getting this replacement for free. So what EWEB allows you, it allows you to store secrets and specify the release conditions. And then possibly other users will be able to retrieve these secrets if and only if they're able to satisfy the release condition. And this is done without relying on trusted third parties. So to give you an example, let's say you have a journalist who is working on some report about a very serious crime. And let's say that this journalist has some information, some very sensitive information about highly influential people. And let's say that the journalist fears for his life. What the journalist can do is the journalist can store the sensitive information with EWEB and specify that the data should be released if and only if the death certificate of the journalist is published on the blockchain. And so in this case, EWEB will allow the journalist to have some sort of insurance and use the sensitive data that he possesses as an insurance for his life. And so hopefully you are very excited about this and are asking yourselves how we can achieve such a primitive. And let me start by telling you that we are using the blockchain miners to store the shares of the secret. However, some of the blockchain miners can be malicious, and so we do not want to simply give a secret to every single miner. What we do instead we are sharing the data to the blockchain miners. And again, we do not want to share the data to every single miner of the blockchain. That would be too much. So instead, we are picking some committees of size, let's say, I don't know, 100, 1,000, and we are secret sharing the data to these committees. Then because some blockchain miners can, join the system, some blockchain miners can leave the system, we will have some mechanism which will allow us to pass secrets from one set of committees to the next. And finally, we will have some mechanism which will allow us to release the data to the party who is eligible to obtain this data. And there are really multiple interesting things about eWeb, but for this talk, I will focus only on the storage and the committee update part. And I will tell you how we are able to achieve those two algorithms. And really, there is a cryptographic primitive which allows you to achieve exactly that, and it is called dynamic proactive secret sharing. And in this work, we were able to do this very efficiently, and so in the remainder of the talk, I will explain to you how exactly we did it. For a second, forget maybe a little bit about the dynamic proactive part. Let's just focus on the secret sharing. So a secret sharing will allow our journalists to secret share the secret to a set of miners. And then we need the requirement that given the T+1 shares, anyone can reconstruct the secret. But given that most T shares, these shares reveal nothing about the secret. And as you remember, we had this issue that some blockchain miners can join, some blockchain miners can leave. So we will need some way to sort of update the committees that are holding the secret. And this is exactly where the dynamic proactive part of the DPSS comes in. So in more detail, a DPSS allows you to distribute a secret to a set of n parties where the set is constantly changing. Any T parties will be able to learn information about the secret. Oh, sorry, any T parties can learn no information about the secret, but any T+1 parties can reconstruct. And DPSS usually consists of 3 algorithms. So there is a setup algorithm, which will allow you to store the secret. There is the handoff algorithm, which will allow you to sort of update the committees. And the reconstruction phase, which will allow you to release the secret. And for security, we have a formal definition in our paper, but intuitively, we say that at reconstruction, the secret can be released, but prior to reconstruction, no information is leaked. And in this work, we introduced a very efficient DPSS scheme, which is called FAB DPSS, stands for Fast Batch DPSS. It supports an adversarial threshold of 1/2, which is highest possible. And so during handoff, it is especially challenging because we need to consider 2 T corruptions, because T parties can be corrupted in the old committee and T parties can be corrupted in the new committee. The adversary for us is fully malicious and adaptive, meaning that the adversarial parties can behave however they want, and the adversary can corrupt parties at any given time. The communication complexity in our scheme is linear, the amortized one, and the non-amortized is O of n square, and the protocol is also concretely efficient. And I will now tell you how we're able to achieve it, and I will start in the semi-honest case, meaning that all parties for now are required to follow the protocol, but can attempt to gain some information about the secret. And FAB-DPSS is based on the well-known degree T Shimei secret sharing. So Henk Riyad had a very beautiful picture that fortunately I do not have. But essentially, you can imagine a degree T polynomial where the secret is encoded at 0.0. And the ith share is f of I. And as you can see, given T shares, no information about S is leaked, but given any T+1 shares, the party could reconstruct the polynomial and hence get the secret. And in the next slides, I will have this bracket notation to denote a degree T sharing of a value R. Oop, what happened here? Wow, there's supposed to be an animation. I'm very sorry about that. Anyway, the foundational idea in FAB-DPSS is that we are using what we call a coupled sharing. And a coupled sharing is really 2 different sharings of the same value. So you can imagine 2 different polynomials which are the same at 0.0. And what you can do now is to hand off a secret. So to refresh a sharing of a secret S, we have the new committee securely prepare coupled sharings of a uniformly random value R. The old committee will receive shares of R, and the new committee will hold on to the other shares of R. But remember, like R and R prime is the same value. The old committee can now reconstruct S plus R, and note that this is secure because R is uniformly random. And so essentially, S plus R does not reveal any information about the secret. And the new committee can then set the sharing of S prime to be S plus R minus the sharing of R prime. And because I is actually equal to R prime, we are getting that S prime is actually equal to S. So we were able to refresh our sharing without sort of modifying the secret. The question now is, how can we prepare these coupled sharings securely? Because as you remember, we do not trust any single party in a committee. However, we do know that at least half of the committee is honest, right? So we do know that there are some honest parties. Well, what we do is we have each party in the committee prepare a coupled sharing of a uniformly random value. And then we will again distribute one part of this coupled sharing to the old committee and the other part to the new committee. And now what you can do is the old committee can simply compute the sum of all the sharings they received. Same for the new committee. And because so first of all, each ui is actually equal to u tilde I. So you get that I is actually equal to R prime. This is because all of the ui's are the coupled sharings. And second of all, there is at least one ui and u tilde I, which is uniformly random. And so our R and R prime are uniformly random as well. So this is how to prepare the sharing securely. I guess now the question is, how can we do this efficiently? Because actually what we are doing is we have like n minus t honest parties. And so right now we are using these n minus t honest coupled sharings to prepare only a single value that we will use. So can we not get n minus t random coupled sharings instead of only one? And here we're using an idea by Darmgard and Nielsen. They're using a van der Monde matrix of size n times n minus t. And the important property of this matrix is that any n minus t times n minus t submatrix is invertible. And what you can do now is you can take all of those sharings of ui, and you can multiply them by this matrix M. And it will give you n minus t sharings of ri. And this works because, as you remember, we had n minus t honest shares for ui, and so they, because the van der Monde matrix is invertible, so any n minus t submatrix is invertible, what you get is a one-to-one correspondence from the n minus t ri's that you get to the n minus t honest ui's that you had in the beginning. So this is how you can generate the random coupled sharings both efficiently and securely. And this sort of finishes off the semi-honest case. In the fully malicious case, we had more issues that we had to take care of. So for example, a party could distribute an inconsistent degree T sharing, or a party could distribute an incorrect coupled sharing. And for details, please take a look into our paper. But just to give you a flavor, we were able to efficiently check many coupled sharings instead of only one at a time using a linear combination. And we were able to use polynomial commitments to transfer a standard secret sharing into a verifiable one. And this is how our scheme compares to the prior work. So as you can see, among the schemes which have the highest possible adversarial threshold of 1/2, we were able to improve the amortized communication complexity by a factor of n, and the non-amortized complexity remained the same. And the scheme is actually also concretely very efficient. So here on the x-axis, you see the committee size, and on the y-axis, you see the duration of a handoff procedure in seconds. And as you see, FabDPSS outperforms the prior work CHIRP sort of every single time, and the difference only grows with the size of the committee. Okay, so just as a recap, by using coupled sharings and efficient batching via a van der Monde matrix, we were able to achieve a very efficient DPSS construction, which was, again, a probably most important building block in building an efficient EVAP scheme, which in turn allows us to achieve all of the exciting applications that I talked about in the beginning, and actually many more. And so if you have any questions, please feel free to ping me over email or ask me here. Yeah, thank you very much for your attention.
Would you recommend, for instance, the previous speaker and they use your proactive secret sharing scheme for changing secrets or handing off to the 10 new bosses that got hired?
Oh, the 10 new bosses that got hired.
Why or why not? Like, would this be the scheme of choice for that kind of scenario?
I guess maybe so. First of all, if the bosses are not changing, then maybe you're better off with the proactive one, because the dynamic one is really to change the set of parties who are holding the secret shares, and then maybe if you don't have that requirement, then maybe you can do something that is more efficient. But otherwise, it's not a bad idea.
The bosses and the 10 bosses get fired and new 10
If they
bosses,
don't, yes, then maybe
new 10 bosses get hired, then
yeah, you want to have some overlap there, so don't get them fired in the same time. Then you will lose the secrets, I think.
I see. So as long as like they don't get fired at the same time, you are fine. Okay, thank you. Any other questions? Yes, in the back.
I'll yell it. If you have more than n minus t pieces of data, is the best thing to do run less parallel multiple times, or is there something better?
I guess it's asking about whether you can do batching if there are multiple instances.
I think you could do batching. So you could do batching probably also if you have, if you want to encode. So like right now we are only encoding a secret per polynomial, but maybe a dealer can have like many secrets. So I think like you can do batching there actually as well. So like this is not the most efficient version. I think you can do further improvements.